Our next unit that we're going to be focused on is heavy reliant on your factoring skills. So we're going to practice factoring a few examples at the beginning of each lesson. Example 1, factor 2x squared plus 11x plus 12. I know a lot of you guys like to use the visual method, so I'll show you that method first. And in order to use this visual method, we take the leading coefficient and multiply it by the constant. So what multiplies to 2 times 12, which is 24, and has a sum of that middle value, which is positive 11. In this case, I'm looking for my factors of 24, 1 and 24, 2 and 12, 3 and 8, and 4 and 6. They're multiplying to a positive, and the solution, or the b value, is positive as well, so I need both to be positive. So I'll notice that positive 3 and positive 8 multiply to positive 24 and add to 11. The next part of the visual method is that people will take the very first term, drop that exponent, and just put it underneath of those two values that we have and see if they reduce. I have a positive 3 over 2x. It does not reduce, so that becomes one of the factors, 2x plus 3. The other one, 8 over 2x, both of those are divisible by 2. 8 divided by 2 is 4. 2x divided by 2 is just an x. So that leaves me with a positive 4 over x, which becomes my second factor. So 2x squared plus 11x plus 12 has factors of 2x plus 3 multiplied by x plus 4. In the next example, I'll show you the bust and the bees method in case you like that one. So that way you have a method that you can choose. I'm still going to start by using the leading coefficient and the constant term, multiplying them, so it multiplies to negative 36, and have a sum of the middle value, negative 13. In this case, I'm looking for my factors of negative 36. Positive 36. Since we're multiplying to a positive and their sum is negative, I need two negative values. So I need negative 1 and negative 36, negative 2 and negative 18, negative 3 and negative 12, negative 4 and negative 9, and finally negative 6 and negative 6. The two factors that have a sum of negative 13 and multiply to positive 36 are negative 4 and negative 9. And now we're going to use those two values to split the middle term. So we start with x squared minus 13x plus 36, and we're now going to rewrite it as x squared minus 4x minus 9x plus 36. And this bust and bees method is so that we can factor by grouping. So I'm going to group the first two terms together, the x squared minus 4x, determine their GCF, which is just x, and write what is left over after taking out the GCF in parentheses. So in essence, you're dividing through by x for each of those. So it's x multiplied by x minus 4. And our back two terms, make sure you take that sign with your third term. And normally, usually, you can count on it, if the third term, when factoring by grouping, is negative, you want to factor out a negative value. So I'm going to divide out or factor out a negative 9 in the hopes that I get the identical factor, x minus 4. Negative 9x divided by 9 is positive x. 36 divided by 9 is in fact negative 4. The whole goal is to have a common factor, which is x minus 4, and then use those GCF factors that we pulled out to become your second factor. So our expression x squared minus 13x plus 36 has factors of x minus 4 and x minus 9. Again, factoring helps us quite a bit and is used quite a bit in Unit 7, graphing our rational functions. Today we're going to discuss the domain, vertical asymptotes, and both the x and the y-intercepts. We're going to have quite a bit of vocabulary at the beginning, so make sure you jot everything down before we actually practice what each of them mean. So a rational function is an algebraic fraction or ratio where both your numerator and your denominator are polynomials. The parent function that we have graphed is y equals 1 over x. A rational function will always have a break in its domain. If you remember excluded values from our previous unit, in the functions, they actually become a vertical asymptote. And you can actually see this vertical asymptote in the function. That's a dotted vertical line, and it actually shows us it has an equation of x equals 0. That value is undefined in the entire function. It does not work. So it's an excluded value, and we draw it as an asymptote. Another thing about our rational functions is it will have at least 2 different sections graphed. It can have more depending on the asymptotes that it has, but you'll have at least 2, as shown in this picture. It will have either a horizontal or a slant asymptote. This example has a horizontal asymptote. It's actually not drawn, but you can see the far left-hand side of the graph is approaching y equaling 0, and the far right-hand side of the graph is also approaching y equaling 0. So this example has a horizontal asymptote. A slant asymptote would be a diagonal line, and it changes the shape of your graph a little bit. And lastly, another thing is that a rational function can, but does not have to have, holes, x-intercepts, and or a y-intercept. And we'll go through the processes for each of these as we go through the entire lesson. Main thing, when you see any rational function that you're going to need to graph or determine any of these characteristics, you want to factor everything, numerator and denominator. Our domain of our functions is, remember, representative of all of the possible x values. So in order to determine the domain, remember it's going to have a break in the domain, or at least have a vertical asymptote. We need to set all of the factors in the denominator equal to 0 and solve for x. That's very, very similar to determining the excluded values that we did in our previous examples and previous lessons when we were simplifying and solving rational equations. In interval notation, your domain is written as -infinity to the vertical asymptote, u for union, and then your vertical asymptote to positive infinity. If it is written in actual words, you can write all real numbers except the vertical asymptote. So you could say something like all real numbers and use this notation with the double R, except x does not equal whatever the value of your vertical asymptote is. So that's another way that you can have your domain written. Those vertical asymptotes are the factors in the denominator that do not reduce. Again, you set those equal to 0 previously to determine your domain. We called them excluded values before, but now in the function, it's an asymptote. It's always going to be x equals a number. And again, these do not reduce. Your x-intercept, where you cross the x-axis, these will be the factors in the numerator that do not reduce, and they're always written as an ordered pair, the number, comma, 0. Okay, so it does ask for an intercept, so make sure you write it as a point. And then last but not least, your y-intercept. You can replace all of the x values in the equation with 0 and then solve for y. It again is also always written as an ordered pair. In this case, it'll be 0, comma, the number. Now we're going to start practicing a few of these. Just look for the thing it's asking for. We're not going to go too far. So determine our domain. Remember, it says factor everything. So even though for the domain, I'm only looking in the denominator, I'm still going to factor the numerator just in case. So the numerator has a 2 in common of the 2x plus 6, and that'll leave me with 2 multiplied by the quantity of x plus 3 all over x. Okay, our note down at the bottom says to determine the domain, set all of your factors. So here's my domain. Set all of my factors in the denominator equal to 0 and then solve. Okay, so right now x just equals 0. That means I can write my domain from -infinity to this value, union that value to positive infinity. Remember, this is the value that's going to be an excluded value. We can't include it. If I substitute a 0 for the denominator, it makes the entire function undefined. So there's our domain written in interval notation. That's typically how we're going to do this. Example 7, f of x equals x plus 1 over 2x squared minus 2x minus 12. I can't factor the numerator, but the denominator I can factor. I'm first going to take out a GCF of 2, leaving me with x squared minus x minus 6. And then when I factor, I'm looking to see what multiplies to negative 6 and adds to negative 1. So that has to be the factors of 2 and 3. 2, and then also negative 3 because I need to add to a negative value. So my factors are 2 multiplied by x plus 2 and x minus 3. So my factor turns in, or excuse me, my function can be rewritten as x plus 1 over 2 multiplied by x plus 1 multiplied by x minus 3. Okay, again, to determine our domain, we're going to take any factor in the denominator and set it equal to 0 and solve. Now you'll notice I did put 2 equals 0. That is one of the factors. It's kind of nonsensical, guys. We know that 2 doesn't equal 0. I just want to show that just to prove to you guys, hey, if there's not a variable, we don't really have to worry about it. If x plus 1, oh, why did I write a 1? Excuse me, I made a big, huge mistake. That should be a 2. Should be x plus 2. My goodness. All right, here we go. X plus 2. So if x plus 2 equals 0, when I solve for x, I get x to equal negative 2. So that's the first break in the domain. And then if x minus 3 equals 0, when I solve, I get x to equal positive 3. These are the places in the domain that it does not work. So we are going to write our domain going from negative infinity from the least to the greatest. So I'm going to go from negative infinity to negative 2. Union. Now I have to go between the asymptotes, negative 2 comma 3 union, and then from 3 up to positive infinity. Make sure that those x values, those breaks in your domain, are in numeric order. All right, one more example. Write our domain in interval notation. The numerator 3 is perfectly fine. Denominator x squared plus x minus 2 needs to be factored. So what multiplies to negative 2 and it has a sum of positive 1. The only factors of 2 are 2 and 1. And I need to multiply by a negative so that the 2 will be negative. So 2 multiplied by negative 1 is negative 2. 2 plus negative 1 is positive 1. Okay, so my denominator factors will actually become x plus 2 and x minus 1. Again, in order to determine the values not included in the domain, we're going to set each of those factors, x plus 2 equal to 0 and x minus 1 equal to 0. When I solve for the x values, I'll get negative 2 and positive 1. Again, put them in numeric order as you actually list the domain. We're going to start at negative infinity, travel to the first vertical asymptote, the least one, so negative 2. We can travel between the asymptotes, so union, negative 2 to positive 1, and finally go from that last vertical asymptote out to positive infinity, 1 to infinity. There you go. All right, we're coming up on the 15-minute mark, so I'm going to stop the presentation and just give you guys smaller bits so you can go to your practice worksheet now and actually practice some domain problems and check your work. Then we'll come back and do the remainder of the lesson.